So now we have seen what search problems look like, we can turn towards search algorithms. But before we describe the algorithm, I need to describe the data structure that we manipulate during the search, and this is called a search node. A search node is really a bookkeeping structure that encapsulates a state. Note that I say search tree here because we will be using the search graph as a search tree. This is simply to make the algorithm slightly easier to explain, but there is a simple extension that you can come up with that turns this back into a graph search algorithm. So here is the data structure we're looking at. Each search node consists of 5 things. The first thing is the state that is encapsulated in this search node. So a state corresponds to a configuration of our world, and a node is a place in our search tree. Note that 2 search nodes may contain the same state. The next component of a search node is the parent node that we store in each node. That is the immediate predecessor in the search tree, the parent in the tree. The only node that doesn't have a parent is, of course, the root node in a tree. Then we have to store an action in a search node. That is the action that gets us from the parent node to this node. Or more precisely, from the parent node's state to this state. Then we also want to store the path cost in a search node. That is the total cost of the path leading to this node in the tree. And finally, we can store the depth in the tree as part of the node, which allows us to do, for example, a simple cutoff if we go too deep in the search tree. So these are the 5 components that make up a search node: the state, the parent node, the action, the path cost, and the depth. So now we get to the first algorithm that you will see on this course. This is the general tree search algorithm. The algorithm is implemented as a function tree search that takes a search problem as input and a search strategy. I will get to the search strategy in a minute. The search problem is simply what we've seen before, the thing that consists of 4 components: the initial state, the successor function, the goal, and the path cost function. The algorithm starts by creating a new search node, so that's the structure we've seen in the previous slide, from the initial state of our search problem. And this is stored in a set of nodes. These are set braces. And the set is called the fringe. It's often also called the set of open nodes as opposed to the set of closed nodes. What this means is these are all the nodes in our search tree that we have not yet explored. And initially, we have not explored the initial state, and that's the only state we know about initially. So what we do then is we go through a potentially infinite loop. And the first thing we do in this loop is we test whether there are still nodes in our fringe that we can examine. If there are no more nodes on the fringe, that means we've explored the whole graph and we haven't come across a node that is a goal node. So in that case, we can return failure. There is no solution to the search problem if we have explored all the nodes in the graph and have not come across a goal node. But initially, there will of course be at least one node, namely the node we created from the initial state. So what we do in the next step then is we take our set of fringe nodes and we select one node from the fringe, and we use the strategy to decide which node we will select first. So this node is the next one we will explore in our search. And by explore, I mean 2 things. The first thing is we apply the goal test to the state that corresponds to this node. If this node is a goal node, that means we've found a solution to our planning problem, to our search problem, and we can stop the search here. Note that this also catches the case where our initial state was actually a goal state, because the first thing we do is we apply the goal test before we do anything else to this node. If the goal test has succeeded, we can simply return the path to that node, as this must be a solution to our search problem. If our current node we are looking at is not a goal node, then what we have to do is we generate all the successors and we use a function expand here to do this. So what we do is we take the problem and we take the node and we apply the successor function that is defined as part of the problem to this node, which gives us a set of actions and new states, and each of these states can be turned into a new node together with the action that led to that state. And we expand the fringe, so we add these new nodes to the fringe, and this gives us our new fringe. And at that point we go back to the beginning of the loop and start again. We look at the fringe whether it's empty. If it's not empty, we select a node from the fringe, so this will be now a node at depth 1. Then we apply the goal test to that node. If it's not a solution, then we have to do the same for that node, expand it, generate its successors, and so on, until we finally come to the point where either we've explored the whole graph, which means the fringe is empty, or we come to the point where a node is a goal node and passes the goal test. And in that case, our search is done. Now, there are a few subtleties with this algorithm that I briefly want to go into. The first one is that a tree corresponding to a finite search graph may be infinite. Look at this very simple tree. We have 2 nodes here, and we can go from one to the other, and then we can go back. If neither of those 2 nodes is a goal node, that would give us an infinite loop. We can always start here, then we add its successor to the fringe, which is this node. Then we have only one node on the fringe. But then we go back to this node, add this to the fringe, we go here, and our search tree will be infinite. So that means that this loop here may never terminate, even if the search graph is finite. And the second subtlety has to do with the strategy, and that's what we will look at next. The search control strategy is an effective method for scheduling the application of the successor function. We have seen this in the algorithm. The strategy tells us which node from the fringe we will select next to apply the successor function to, and generates its successors. Now, the first thing to note here is that it's got to be an effective method. So what we mean by that here is that the strategy must not take up too much time to decide which node from the fringe to expand next. Ideally, it would take constant time. What the strategy then does is determine the order in which we expand nodes, or the order in which we explore nodes in our tree, the order in which we go through our tree to look for a goal state. Our aim, of course, is to produce a goal state as quickly as possible. So we want to descend down our tree to a goal state that is relatively close, and we come across that quite quickly. So a perfect strategy would know where that goal state is in our tree, but then if we knew where the goal state is, we wouldn't have to search for it in the first place. In general, a strategy that produces a goal state quicker than another is considered a better strategy. And the way we have described the algorithm in the previous slide, with the strategy as an argument to the node selection, this makes it a deterministic algorithm as long as the strategy is deterministic. Otherwise, without the strategy, you can read this as a non-deterministic algorithm. The way a strategy can be implemented is by keeping the fringe nodes in a specific data structure. A queue could be either a last in, first out queue or a first in, first out queue, and that results in different search algorithms. For example, the LIFO queue is effectively a stack, which means our search proceeds by always exploring the node that has last been added to the queue, which means it does a depth first search. It goes deeper into the tree before it examines the neighbors of a given node. FIFO would give you a breadth first search by going to one level of the tree before it goes to the next. But there are many, many more ways you can think of how to search, and we will look at something called a heuristic in the next week. Just another example, you could also take an alphabetical ordering of the nodes if you can find some ordering relation between the nodes. Another thing that is quite important is that in many search problems, the complete tree is far too large to fit into a computer's memory, even with the kind of memory we have today. So the search strategy determines which part of the search tree will be explored and will be in memory. And therefore, it may determine whether we are successful at all, because if the search tree is too large for memory, we may not come across a goal node at all. Now, for those of you who are not familiar with search, I recommend that you either go to the Russell and Norvig textbook that is mentioned on the website and have a look at the corresponding chapters, or you should go through a little programming exercise and implement the missionaries and cannibals problem as a search problem. You can use either of those two queuing strategies mentioned there, last in, first out, or first in, first out, and just see what happens when you apply these two strategies. Also, a hint regarding repeated states. To turn the tree search into a graph search, you have to remember all the nodes you've seen so far, and the most effective way to do this is to add them to a hash table. And before you add a node to the fringe again, you check whether it is already in that hash table. You should be able to do this in the programming language of your choice. The missionaries and cannibals search space, as you have seen, is very small, so the search should be instantaneous, whatever you use. So, have fun with that.